lecture 14 in statics. If you had looked at our Moodle page before, you'll see that I had lectures 14 and 15, but I'm combining them into this lecture. So this is actually the last lecture for chapter 14, and we're going to talk about equivalent force couple systems, which is section 3.4, and then we will work a couple of problems. Now there's only going to be 2 additional problems, well, 1 problem and then 3 parts of another problem for this section and to finish our homework. But I am going to extend the homework deadline for all of it until Monday. So if you've got the rest of it done, you're almost done. These 2 problems will be relatively quickly. They're both 2-dimensional problems rather than 3-dimensional problems, so that definitely decreases the math load. And then also, there's only 2 of them, so I think you're going to be just fine. So if we take a look at the first thing I'm going to do is to do a short lecture on this content. And what we're talking about here is how to reduce a system of forces. And we talk about reducing a system of forces. What we mean is if we have a multi-force system, you can see here that we would have 4 forces, and then we would have 2 reactive forces. So there's a total of 6 forces. Everything has to balance out in terms of force, and then it also has to balance out in terms of moments. So to solve a problem like this where it says find the resultants and the resultant couple about some point. Now that means we have to determine a point. So we go back to some just good statics where we take the forces that are applied and we come up with the resultant of those forces. Now how do we determine the moment about A? We have to choose point A, and then we take the distances and the force, each distance and each force from point A, and come up with the value of the moment that would occur about point A. So in other words, this beam shows an equivalent applied force and moment scenario to the one above. So here we have 4 forces. Here we have reduced that to just a force and a moment. So the process in each of these is to do statics, to find the resultant of those forces, and then to find the moment that results from the original forces. So here we start with the original diagram and reduce it in the second diagram. All right, so here we have a situation where it says find an equivalent force couple system at B. We have this moment at A right now, don't we? All right, and so we need to move it to B. So basically what we're saying is we're going to take this 600 Newton force and move it to B. That keeps our force system the same, but now we're going to have something different in terms of the moment. We still have this moment, but now we're going to have some other moment based from moving this force 600 times 4.8 meters. And so there's that. So we combine these 2. We just take directions. And since this is 2-dimensional stuff, we add these together. We add negative 1,880 Newton meters to positive 2,880 meters. And we get a couple in the amount of 1,000 Newton meters. All right, we're not going to do any 3-dimensional stuff. So that's kind of all of the material that we have in terms of our lecture. Now what I'm going to do next is to solve a couple of problems. So we'll take a look over here on the document cam, and for homework I'm going to put up on the page that you'll be doing problem 106 and 101 parts B, D, and F. So I'll do 105 and 101 parts A and G. All right, so first of all, let's take a look at problem 101 in your textbook. And what you'll see is that 101, and this is very faint, let me see if I can zoom in a little bit, shows a series of beams that are being loaded with forces and moments. And in each case, it tells you that the beam is 3 meters long and subjected to a variety of loadings. We want to replace each loading with an equivalent force couple system at end A of the beam, right here. Then it asks you which loading are equivalent. Well, the answer would be after you did all of them, if two of them looked identical to each other, they would be equivalent. However, you're not doing all of those. You're just going to be doing parts B, D, and F. So you can just examine those parts, and I'll do A and G and examine those as well. All right, so getting back to it, when we take a look at part A, we have a beam that looks like this, and we have a 400 Newton meter clockwise moment on that beam, and we have at point A a 300 Newton force, and at point B a 200 Newton force. All right, so the first thing that we want to do is to find the resultant of those two forces by summing the forces. They're both y directions, so we can say the summation of forces in the y direction is equal to the resultant force. So here that would be negative 300 newtons minus 200 newtons equals R, or negative 500 newtons equal R. All right, so that is the first part of our journey. And the next is we want to place that. We want to place it at A, but we want to replace both of these forces with the resultant force. And I'm moving it to point A because when we do that, that force is no longer going to be making a moment, because the moment about point A is the force times the distance. So since the specifications calls for an equivalent force couple system at A, I move that force to A, and then I want to go back to my original drawing and decide what's going to be happening with this 200 Newton force. In other words, when I do the summation of moments about A equals the resultant moment on this, and I should say at point A. Okay, so we have the free force, which is 400 Newton meters. The spin is clockwise, so it's negative. And if I put a pin here at A, I see that this 200 Newton force would also create a clockwise spin. So it's 200 newtons times 3 meters, because the distance from here to point A is 3 meters. So the resultant is going to be minus 400 minus 600, or minus 1,000 Newton meters. All right, so what that means is that if we move this to point A, then this is going to be a minus 1,000 Newton meter moment in the clockwise direction. So what that means is that replacing these two forces with a single force at A, that is the resultant of those two, and adding any moments that are still on the original loading configuration to the existing applied moments, putting them both at point A, will be an equivalent system. All right, so the next one that I would like to do is G, which is more of the same, slightly more complicated, but not too much. All right, so for problem G, we have a beam with supports. We have an 800 Newton force applied here at A. We have a 300 Newton force applied upward at point C, which of course is 3 meters away. We have a 1,000 Newton meter force, which is counterclockwise, and a 400 Newton meter force, which, I'm sorry, this is counterclockwise. They're both counterclockwise. Okay, so there we go. All right, so these are both positive moments, aren't they? Oops, I got to spin this out a little bit. Sorry. Let me get this. There we go. All right, so going through that again, this is problem A, or part A. This is part G. So we have an 800 Newton applied force at point A, a 1,000 Newton meter moment, and a 400 Newton meter moment, and then a 300-pound force at point B. So to move everything to point A, we want to move this to point A, essentially. And so if you think about it, we could just add them. This is negative, this is positive. So the force at A then is just going to be negative 800 plus 300, which is a negative 500 Newton force. So this is equivalent, which is interesting. Don't know if the moments are going to be equivalent. The first thing that I'll need to do is to add, or to decide then, the moments, summation of moments about A is equal to the resultant moment at A. We have a counterclockwise 1,000 Newton meter force. We have another counterclockwise positive excuse me, I said force, I meant to say moment. We have a 1,000 counterclockwise Newton meter moment. We have a 400 Newton meter positive counterclockwise moment. And then this force, this 300, is also producing a counterclockwise moment about point A. The distance here is 3 meters. So if I add these two together, I get 1,400. And this number, 300 times 3, is 900. The units are Newton meters. And so this is a 2,300 Newton meter counterclockwise moment placed at point A. So that means that the equivalent moment is going to be 2,300 Newton meters counterclockwise here at point A, and this system is equivalent to this system. Now, if you look here to my original problem, the force system, the force part of the system is equivalent, but the moment part of the system are not. So A and G are not equivalent. All right, the next problem I will do is 3.105, and this is sort of a classical statics force couple system as well. So what we have is two children on a teeter-totter. We have child A weighs 84 pounds, child B weighs 64 pounds, and we want to know where a third child should sit so that the resultants of the weights of the three children will pass through point C. If that child weighs 60 pounds and if that child weighs 52 pounds. All right, well, the first thing is this kid weighs more, so he's going to tend to pull the teeter-totter in a counterclockwise fashion. This child weighs less. She's going to tend to pull it, she or he, it looks like a she to me, is going to pull it in a clockwise fashion. So we need more of a clockwise moment. That means that wherever that child sits is going to be over here on the side with child B. When it says, so the resultant of the weight passes through C, what we're really asking here is when the counterclockwise moment of this kid will equal the clockwise moments of the two kids over here. So what we have is a 6-foot distance, and this kid A, the moment from kid A is always going to be the same because he always weighs 84 pounds and he's always 6 feet from point C. So if we take 84 and multiply that by 6, we get that the moment that he creates about point C is 504 foot-pounds. Okay? So what we're saying then is we want this first kid, who is 64 pounds, her weight 64 pounds, times her distance of 6 feet. Going the other way, she will always produce a moment about point C of 64 times 6 equals 384 foot-pounds. All right, so what we want to do is get a moment that's the difference between these two by the other kid. So the moment for the third child must be 504 minus 384, which equals 120 foot-pounds. Okay? So how do we produce a moment when the child has a fixed weight? Well, first of all, the first kid has a weight of 60 pounds. So how do we produce a moment? We have to create a distance that's going to give us a moment of 120 pounds. So if we take that D is going to be 120. This is foot-pounds. Sorry about that. There we go. So this distance is going to be 120 over 60, which is 2 feet. All right, so that means that in this case, to produce that kind of a moment, in case A, a 60-pound child must sit 2 feet to the right of point C. All right? And then in the second case, we're told that the child weighs 52 pounds. So it's a similar process. 52 times D still has to equal 120 foot-pounds. So in this case, D is 120 divided by 52. 120 divided by 52 equals 2.307. So I'm just going to call it 2.3 feet. All right. So in this case, B, a 52-pound child must sit 2.3 feet right of C. And the answers kind of make sense. The heavier child sits closer to the pivot point, while the lighter child would sit farther away from the pivot point. The other thing that one should check is to make sure that these distances actually are on the teeter-totter, which they are, because from C to the outside edge is 6 feet. And if we had a really light child, we could put that child on the back of, like, could sit behind this girl and would produce a greater moment, because once again, a moment is a force times the distance. All right, so everybody, that is the end of our material for Chapter 3. I'll post these 2 problems. I will edit the due date for the homework, and then we will see you again Monday for our beginning adventure with Chapter 4. Thanks.